periodic vibrational motion is everywhere in nature. There are all kinds of systems that exhibit this property of motion where it occurs over and over again like a cycle, periodically. And the classic system to study is an oscillating spring. So we've seen a little bit of this before, like where we have a mass attached to a spring and we stretch it and let it go. What the system does when you let it go is it oscillates back and forth. You stretch this mass out, this block out. You let it go, the spring applies a force opposite to the direction that it was stretched. That's Hooke's law for the force. And it begins this oscillation process. So it goes to the left, passes through equilibrium, the spring gets squished, and then it starts to push the spring to the right, and this process occurs over and over again. So this system itself is not necessarily that interesting. Like, we don't really care that much about springs. They're useful for some things. But once we can understand this process mathematically, it turns out that the math is identical for all sorts of other things in nature. And we'll start here, we'll get these tools down, and then we'll see examples of all sorts of other things that we can use the same math for. All right, so let's take a look at the system, and we'll think about what's happening with the force. We'll think about what's happening with potential and kinetic energy, and then we'll do a little calculation. So as I mentioned, and as we've learned before, the force this spring applies is proportional to the distance that the spring is stretched or compressed. That proportionality constant, K, is known as the spring constant or the force constant. And there's this magical minus sign in there telling you that the force is opposite to the stretch. So if this spring has a natural relaxed length, giving you an equilibrium position right here, and we pull it to the right, that means there's a force pulling in the opposite direction from the spring. There's a force directed to the left. So there's the force vector for that first picture. In the second picture, the spring is still stretched a little bit. So it's still getting pulled to the left, not quite as much as before. In the third picture, the spring is at its equilibrium position, so there is no spring force right here. But this block already has some velocity, so its inertia carries it forward until it gets compressed, and the amount that it gets compressed, this distance, which we're calling A, is the same. It's symmetrical to the right and to the left. It's symmetrical on either side of the equilibrium position. So that A, that amount of stretch, is known as the amplitude. So if we pull positive A and let it go, it gets compressed to negative A. And when the spring gets compressed, it applies a force opposite that compression. Sends the block going to the right. It passes through equilibrium again, where the force is 0, but the block's inertia carries it to the right until it returns to that starting position. Now, we've looked at the forces for each of these pictures. Let's think about the speed or the velocity for each picture. Initially, that velocity is 0. At the ends, at those extreme points, the block is stationary. Now we let it go, and we we've got a velocity vector pointing to the left. At this equilibrium position, we have the largest magnitude of velocity, the largest speed. At the turnaround point, v is 0 again. And as we pass through equilibrium, we again have that large v max, just headed in the other direction. Now let's look at all these pictures and think about the energy, kinetic energy and the potential energy. In the first picture, the spring is stretched to its maximum and it's stationary. So we have potential energy that's at its max. We could even, if we wanted to, substitute A into this expression, 1/2 kA squared. So rather than saying max, let me say that potential energy here equals the total energy of the system. And the KE is 0. In the second picture, we have some mix of potential and kinetic energy. The spring is still stretched, but the block is moving. So we have some mix. And those two added together give you the same total amount of energy. At the equilibrium position, the spring is not stretched. And so that all the energy is kinetic. The total energy of the system is now purely in kinetic form. But that kinetic energy has the same value as the total energy it's had the whole time. In this picture, all the energy is potential. The block is momentarily stopped. The spring is at its maximum compression. And in this picture, again, all the energy is kinetic. The spring is at equilibrium, and it's not stretched or compressed, and it's moving at its fastest speed. Okay, so let's use these concepts to do a little calculation. This is example 13.4 from your textbook. Let's consider a system that has these values. M equals 0.5 kilograms. The spring constant is 20 newtons per meter, and the amplitude, that initial stretch, is 3 centimeters, or 0.03 meters. So let's answer a few questions. What is the total energy of that system? Well, we saw before that you can find the total energy because it equals the potential energy at that maximum stretch, because all of the energy at this position is in potential energy. The block is stationary right there, so there's no kinetic energy. So E total equals that potential energy at the maximum stretch, which is 1/2 K times the amplitude squared, and that has a value of 9 times 10 to the minus 3 joules. Another question we might want to know is what's the speed as the block passes through equilibrium? Well, we know at equilibrium, the total energy is purely kinetic. The spring isn't stretched, so all of that energy is from the motion of the block. So we can say the total energy equals 1/2 mv squared, and that maximum speed would be 2e over m square root, which gives you 0.19 meters per second. Now, one more question that we'll answer. What is the speed when that position is 2 centimeters? So that would be kind of like this picture. We stretched it out initially to 3 centimeters, and we let it go, and it moves to 2 centimeters. So at that position, we're not at equilibrium, we're not at the maximum position, we're somewhere in between. So the total energy is a mix of potential and kinetic. So we need to say that E is PE plus KE right there. That PE is 1/2 K x squared, where x is 2 centimeters. And KE is 1/2 mv squared, where v is what we're solving for. So that's our unknown. We've got to do some algebra to get there. Something like that. And you plug in those values and you find that this is plus or minus 0.141 meters per second, because when you do a square root, you get plus or minus. And let's interpret those plus and minuses. That's saying that this actually works whether you're 2 centimeters to the right of the equilibrium point, or if you were 2 centimeters to the left of the equilibrium point. And if you were 2 centimeters to the right, that velocity should have a negative sign. If you're 2 centimeters to the left, that velocity should have a positive sign.